Okay, to follow up on what we started in class, we're going to go through a process for factoring all different types of quadratic expressions. So just to go over what a factor is, to recall what that is, for instance, you learn the factors of 20 are numbers that divide evenly into 20. So we've got 1, 2, 4, 5, 10, and 20, and also the negative versions of those. The factors of 12 are 1, 2, 3, 4, and 6. And the negative versions of those. So let's list the factors of 10. We've got plus or minus 1 goes into 10, plus or minus 2, plus or minus 3, no, doesn't go into 10, 4 doesn't go into 10, but 5 does, and then plus or minus 10. 24, got 1 divides into 24, 2 divides into 24, 3 divides into 24, 4 divides into 24, 5 does not, 6 does, 7 does not, 8 does, 9 does not, 10 does not, 11 does not, 12 does. Once we get to the halfway, the only last one is 24 itself. So let's define what a factor is. A factor is a number in this case, but it can be a quantity or even an expression when we start factoring expressions. That when multiplied, with another factor, gives a number or expression. So we're going to look at these boxes below, these expressions. Oh, and by the way, so factor, we want to really just, it's about the multiplication. And sometimes because it's multiplication, we have to do division to figure out what it is. As you saw up here, I can find factors by doing division because that's the kind of the inverse of multiplication. So each of these is called the quadratic expression because of something they have in common. This is, was supposed to be more of an investigation. Look at each expression carefully and talk with a partner. So I'm just going to kind of give that to you. The quadratic expression is any expression whose largest exponent is 2. So you can see the exponent of 2 being the largest exponent for each one. That's what makes it quadratic. An expression means that it's not an equation, doesn't have the equals anything. All right, so we're just dealing with expressions. Based on the definition of the word factor from above, determine if the following expressions are pairs of the quadratic expression. Show your work. So are 2x and 3x minus 4 both factors? Well, if they were both factors, based on our definition, if we multiply them, we should get the expression that we're seeing if they're factors of. So when I multiply 2x times 3x minus 4, I have to use distributive property, so I get 6x squared minus 8x. That matches that, so yes. Okay, so I would like you to pause the video now and do the other 5 remaining ones, and then see if you get them right. I'll have the answers when you come back. All right, so welcome back. They were all factors, so you get a little practice with distributive property here, and you can see that when you multiply them back out, you get the original expression. So yes, they are all factors. Now remember, what it means to write something in factored form means to find its factors. Multiplication. This is not multiplication, it's addition and subtraction. In this case, it's just all subtraction. This here is multiplication between these two factors. One factor times another, so that's called factored. When we say to factor an expression, that's what we mean. Find its factors and write them as one times the other. All right, so the first method is factoring out the greatest common factor. We did this just before midterms, so let's just review this. When asked to determine the factors of a quadratic expression, I'm not going to read to you. You can pause and read this. Okay, so what mathematical operation do you perform when doing the distributive property? Or you should pause and read it. Okay, so welcome back. What mathematical operation do you perform when doing the distributive property? It's multiplication. To do the reverse of the distributive property, you would do the inverse operation of division, the inverse of multiplication, which is division. So when we're trying to figure out what our common factor is, or we're trying to find out what the factors are, if we know one, we divide it out and we get the others. So use the reverse of the distributive property to determine two expressions that multiply to give us that. So we've done this again. We're looking for common factor. So there's two terms. What is common in each term that divides out of each one? So that's what we're looking for. I can divide a 4 out of the 4 and the 12, and I can also divide an x out of the x and x squared. So that is my common factor. So that's one of our factors. So now I know I can write, I'll write it over here. I know that I can rewrite 4x squared minus 12x as 4x times something else. Okay, 4x times something else. So how do we find out that's something else? Well, first of all, since there's two terms in the original, there's going to be two terms in the second factor when we do common factoring. And what we're going to do is we're going to divide those out. So it goes back to 15. If I know 15 is 5 times some other number, some blank, that's kind of what we have going on here. 4x times a blank. How do you figure out the blank? We just know it to be 3. But what operation would you do? You would take the original 15 and divide it by 5. Sorry. Take the 15 and divide by the factor you know, and this is how you get the 3. 15 factors into 5 times 3. So we have to do the same thing here. So I'm going to take my original on the side, and I'm going to divide each part by the factor I already know, since there's multiple terms. And that's why I get two terms in here. The first term is that first division. So 4x squared divided by 4x, well, 4 divided by 4 is 1. X squared divided by x is just 1x. Over here, negative 12 divided by 4 is negative 3. And then x divided by x, they cancel out, so it's minus 3. That's how you common factor. Okay, let's try again. Let's do the next one. What does it say here to do? Use the reverse of the distributive property. Determine two more expressions that multiply to get 4x squared minus 12x. So we picked the greatest common factor. I kind of skipped right to that. We're gonna skip this part. We already kind of did greatest common factor. All right, so now for each of these, we're going to factor out the greatest common factor. So we'll do these together. There's two terms. If I look at what's the factors of 12 and 6, and we want to pick the greatest one. So the greatest common factor, so like 2 is a common factor of 12 and 6. Right? 2 divides into 12, 2 divides into negative 6. But it's not the greatest common factor. 3 is also a common factor of 12 and negative 6. So the greatest common factor is 3. Okay, so when we decide between 12 and 6, we say 3 is our greatest common factor. And then between x squared and x, well, the factors of x and x squared are x. Those are what they have in common, and that's the only one. I can divide x into x squared because there's 2 of them for me to divide one out. And I can divide x into x because there's 1 to divide out. I cannot divide 2 x's out of that guy. If I only have 1 x, I'm trying to divide out 2. I can't. That's too many x's to divide out. Yes, I can divide x squared out of x squared, but I can't do it out of the other one, so it's not a common factor. So x is the greatest common factor. So that's how you decide your greatest common factor. You go do numbers first, then x is next. So there's my first factor. Now I want to say that factor times some blank gives me the original. So again, how do I find that? On the side, I take my original and I divide by the factor I know. I'm writing this in a different way. This time I'm not putting it divided by each one. I'm showing you could write it like this, but because there's 2 terms up top, you have to do it twice, and you'll get 2 terms in your second factor here, or your leftovers. So there's our first factor. Here is our second factor. So I divide 3x, so 12x squared divided by 3x. 3 goes into 12 4 times. X goes into x squared once, so we have 4x left over. That's our first part. The second one is negative 6x divided by 3x. So I'm just dividing the common factor into both parts. A negative 6, 3 goes into negative 6, negative 2 times. X and x cancel, so I have minus 2. That is how we do factoring by greatest common factor. All right, the greatest common factor here is 5. I could, out of 5 and 10, and out of x and x squared, I can divide out an x. Right? I can't divide out an x squared because this doesn't have enough x squareds to give. So there's my first factor, my common factor. We call that the common factor in this method. The second one is going to be what we call our leftovers. That's what we get after we take and divide by the common factor. That produces our leftover factor. All right, so 5x divided by 5x is 1, right? That's just 1 times 1, so I get a 1. 5 divides into negative 10, negative 2 times. X divides into 2 x's, so there's 1 x left. This is how our two factors of 5x minus 10x squared. Remember, it's our first factor and our second factor. Now, a note of what's happening here. We found two factors, 5x and 1 minus 2x. If we multiply those factors, I get back to the original. That's called factoring. When we write multiplication, sometimes we write parentheses, other times we don't. Why do I not need parentheses on this factor? Because, let me just write it down. No need for parentheses. Because it is one term. It's a monomial, only one term. If there's more than one term, we need parentheses, okay? When we're multiplying things together. Things like this x plus 3 times x minus 2, that is incorrect because that means I'm just multiplying the 3 times x minus 2. If I want to multiply both factors completely, I need parentheses. So whenever there's two terms and you mean to multiply all of this together, you need parentheses around both. Notice in common factoring, typically the first guy is only one term, so we don't need parentheses. Right? We don't need parentheses on that 3x. We don't need parentheses on that 5x. All right, let's keep going here. So if I decide that 2 and 5 have no common factors, the only common factor is 1, I guess we'll say. So let's say 1, and then let me give myself some space here to do the division. 1, and then if I look at the x squared and the x, what's common there is x. I can divide out an x out of both of them. I cannot divide an x squared out of both. This one does not have enough x's for me to divide an x squared. All right, so we've got 1x times whatever we have left over. So our second factor we're going to figure out by dividing the first factor that we know. So this is like a 1x, right? So 2 divided by 1 is still 2. X squared divided by x leaves 1x behind. 1x divided by 1x means they completely cancel, and I have negative 5. I don't need to show that 1 in front. There is how we factored that. We say that we factored out an x is what we say. Right? Some of the language is we factored out an x. We took an x out of this term, and we took an x out of that term, and we just show what it is we took out there. That's our factor. All right, so I want you to pause the video and do these three on your own. All right, welcome back. So you can check your answers here. I've put the answers on. See if you got those right. If not, you ask me about it in class. All right, so now we're going to get into a different method where we say factoring a difference of two perfect squares, where we say factoring quadratics of general trinomials, and then we're going to look at completely factoring. We did this in class, and you guys were doing very well with that game. So these are all like different kinds of methods. They're considered different things, different types of trinomials, and we try to make a method for each one. But what we were doing in class pretty much works all the time. You just got to find combinations of things that multiply. So what we're going to say is, for difference of two perfect squares, that means when your trinomial is missing the linear term, that means the x term. Right? There's no like plus 3x or plus 5x, so the linear term is really 0x. We call that a difference of two perfect squares because when this happens, that means the first guy is a perfect square and this last guy is a perfect square. And it's called difference because of the subtraction sign. So when you see a difference of two squares, we're going to know how that factors immediately. There's a shortcut. I know we can use the process we used in class by just trying to figure out what multiplies to that, but there's a shortcut if you could recognize this. So we're really talking about just jumping to a shortcut. So as for practice, they want you to multiply these binomials out and see that the result we get always produces a 0x mixture term. I was calling that the mixture, right? It always produces a 0x for all of these factors, and that's why we get a difference of two squares. So let's go 2x times 2x, we get 4x squared. 2x times negative 3 gives me negative 3x. That's our first part of our mixture term. So actually, let me write this out because this is the language I was using in class. If this is the first and the last part of the first factor, and this is the first term and the last term in the second factor, to get the first first term, we multiply our first times our first, gets us the first guy. We do our last times our last to give us the last guy. We'll leave some space. 3 times negative 3. Now we do the mixture. We do the first times the last. That gives us our negative 3x. And then we're going to mix that with our last times our first, which gives us the positive 6x. So sorry, our first times our last here is not negative 3x. It's negative 6x because I had negative 2. Positive 2x times negative 3. So I get a negative 6x and a plus 6x. So there's the mix part. I have to now mix those together. And notice that they equal 0. So now I just get 4x squared minus 9. And what there is to notice here for this shortcut is that if these are perfect squares, the first term is the square root. The first term in each are the same, and it's always the square root of 4x squared. The square root of 4 is 2. The square root of x squared is x. The square root of 9 is 3, so that's the last terms, and there is no middle term because the signs are opposite. Okay? So let's look at the next one. Because the signs are opposite, the firsts are the same, the lasts are the same, and the signs are the opposite, I know that when I multiply these out, I'm going to get the first times the first and the last times the last. The middle terms will cancel out. They always add up to 0x. Right? If I do this out, I got x times x is x squared, x times 5 is negative 5x. I'm doing the distributive property. 5 times x is 5x. 5 times negative 5 is negative 25. These cancel and you arrive at x squared minus 25. That's called a difference of two perfect squares. You'll know that it always multiplies by that. You have to recognize this. Now, you don't have to. You could always just do it out like this the long way. But you should start to recognize when you have these conjugate pairs that when you multiply conjugate pairs, you get a difference of two squares, meaning the 0x term in the middle goes away, and you just square the first guy and you square the last guy. So I squared the x to get x squared. I squared the 5 to get 25. That always happens when I have conjugate pairs. These are called conjugate pairs. If I multiply conjugate pairs, you always get a difference of two squares. Why are they conjugate pairs? The first term matches the first term. The last term matches the last term, except they differ by their signs. One's positive, one's negative. That's a conjugate pair. Whenever you multiply those, you always get a difference of two squares. So in this case, I know that if I multiply these out, I just have to do the first times the first to get 9, and the last times the last to get negative 25x squared. Why did I not have to do the mixture term? Because when I recognize conjugate pairs, I know the mixture term will cancel out. Look, 3 times negative 5x is negative 15x, and then 5x times 3 is 15x. Those will cancel. So the shortcut here is recognizing conjugate pairs. So what do all the factors have in common? They are conjugate pairs. You have to know what that means. It's going to come back as well later in the course, later in this unit. All right, what do all the results of multiplying the binomials have in common? They become a difference of two perfect squares. So now we want to factor these. We want to go the other way. We notice that if we multiply conjugate pairs, they always come out to be difference of two perfect squares. Now we want to say if our original thing is difference of two perfect squares, if we have to factor and we recognize it as a difference of two squares, we just know that it automatically factors into the conjugate pairs. All right, so let's make a little process here. When factoring a quadratic, there are three things that we have to do at this point. The first thing I recommend is put the factors in order. You don't have to do this. Sorry, not the factors, put the terms. In order from largest exponent to smallest. I'm out of room. Exponent. You don't have to. This one's optional. I don't do this usually. Sometimes I do, but most of the time I don't. Step 2, you need to factor. You always try common factor first. Factor out the greatest common factor. Step 3, check for difference of two squares. That's if you want to use these shortcuts. Otherwise, you can just start doing the method we did in class during playing the factor card sort. But these are shortcut steps, okay? So if you notice that it's a difference of two squares, you can jump right to the answer. You don't have to start figuring out like you did for the card sort. So let's try this here. First of all, is there a greatest common factor? Yes, there's a 2 that I can factor out. So if I divide both of them by the common factor of 2, I divide here, I get just x squared left. If I divide here, I get minus 4 left. Now, I'm not done factoring yet because this is not a linear factor. We want to try to get down to linear factors if we can, right? They're quadratic because the highest power of x is still 2. So, from here, I notice, wait a sec, I got to factor this down now. So I keep track of the 2, and I say what times what gives me x squared minus 4. Well, I notice that, hey, this thing is a difference of two squares. It's missing that middle term. It's got plus 0x, right? And it's got subtraction, so that makes it a difference, and each one is a perfect square, meaning I can square root the first guy. The square root of x squared is x, so I know it's going to factor into x and x. The square root of 4 is 2, so I know it's going to factor into 2 and 2, and I know because the middle term is 0x that one's going to be plus and one's going to be minus. So you just used a shortcut to factor this thing. I noticed that it was a difference of two perfect squares. Let's try the next one. A common factor here is whenever the first factor is a negative, we do want to make our common factor negative. So the common factor between these is negative 3. Let me give myself some room again. Okay, so that's what I'm going to divide out. Negative 3 times what? There is no common factor x because this guy is missing an x. Right? There's no x's here. So the only common factor is negative 3. When I divide both of these by negative 3, negative 3 divided by negative 3 is positive 1, and there's still the x squared. 27 divided by negative 3 is negative 9. So now I still have a squared here in this factor, so I can factor that even further down. So I still have the first factor, negative 3. Now I can take x squared minus 9 and break that into two linear factors. I don't want quadratic factors. I say, hey, wait a second. I see the difference here, the minus sign. There's only two terms. I'm missing the middle term, which means it's 0x. So now it could possibly be a difference of two squares. I have the difference. If that's a plus, it's not going to work, but it is a difference this time. The square root of x squared is x. The square root of 9 is 3. So, whoops, I'm sorry. So I want to write the x in both spots for the first. So the square root of the first x squared is x and x. The square root of the last 9 is 3 and 3. And because there's the 0x in the middle, I know these have to be opposite signs. All right, so you're going to pause the video and try to do all of these yourself. All right, welcome back. So something to note that here is I did not put these in order from largest to smallest. I don't really do that. So you can if you want to. It will change your answer around a little bit, and I can show you what the answer would be. So this guy to notice also is when I divide out my common factor, this is not a difference of squares because the x is not squared. 9x is not a perfect square. So we're just done. Remember, the point of factoring further is that I want to get linear factors whenever I can, right? So linear means power of 1. Notice that this is already a linear factor, so I don't need to factor it further. The only factors that I don't really care if they're linear or not is the monomials, like these guys up front. If this is an x to the 4th or something, I don't care. But these factors that are binomials, 2 terms, we kind of want those to be x to the 1st. So if you notice, I didn't have to go further on this one. It was not a difference of 2 squares. Now, if you actually reverse these like I said is optional first, then your answer would have come out to be this. Okay, let's look down here as well. This one was already in the proper order, but now notice that the resulting did have an x squared, and it is a difference of perfect squares. I can square root 4x squared. I get 2x. I can square root 1. I get 1. And it is a difference because of the minus, and because there's that missing term. There's no plus 0x. Right? I'll write that a little neater. There's no plus 0x. So that's why I know it's this. These signs are the opposite. All right? On this guy, again, I didn't reverse the order, and also notice that when I do my common factor, I already have a linear factor in here. It's not a difference of 2 squares. It looks like it is because you can square root 1, you can square root 4, and there's a subtraction, but you can't square root the x and get, you know, a whole or integer expression, I'll call it. I don't know. But when you have x squared, you can square root it and it becomes x. If you have x and you square root it, it's just square root of x. You don't get anything else. So, and again, the main thing is here that it's a linear factor, so that's why I don't have to factor further. Notice that it's not in the order. I didn't switch the order, so if you did switch the order and called it that, then the answer you would have gotten would have been negative 15x times 4x minus 1. This last guy here, after I factor out the 2, this was a difference of 2 squares because look, I've got a x squared now. So the square root of 1 is 1. The square root of 25x squared is 5x, right? Because the square root of x squared is x. And then because I've got that minus, it's a difference, so that makes these opposites. And also lastly, just a reminder, I'm missing the plus 0x term in there. It's not there. Now, if you wrote this, if you took my suggestion and wrote this, or did the option of writing it from highest power to lowest power, the first thing you're going to factor out is a negative 2. Whenever you start with a negative, you're going to factor out a negative, and your answer would have been this. Now, when you do these difference of squares, does it matter if the minus factor is first and the plus factor is second, or vice versa? It doesn't, because the operation here is multiplication. So if I switch these two factors, it makes no difference. All right, now let's look at factoring trinomials. So these are when the middle term is not 0x. So now we have 3 terms. That's why it's called a trinomial. And this is what we did with the factor card sort. And this video is getting a little long. We're approaching a half an hour. So I'm going to stop here and we're going to do some of this in class together.